Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. So, for more details, you can visit our website www.sapienceeducation.com. Now, from here, I will discuss about the nucleus chapter. So, I have already completed first part of this video, and I am going to discuss about the part two video of this. Right. So, in this the topic which I will discuss is the mass energy and the nuclear binding energy. What is mass energy? Now, Einstein showed that the mass is another form of energy, and one can convert mass energy into the other form of energy. Einstein mass energy equivalence is this: E is equal to mc square. So as he has came to the E is equal to mc square. It means that mass can give you the equivalent amount of energy. Mass can give you the equivalent amount of energy. Amount of energy. But one thing it is to be noticed that energy, if m is the mass, if there is a body and it has a mass m, and c is the velocity of the light, and if c is the velocity of the light, and if it is moving with the velocity of light, and c is the velocity of the light, so energy of this object will be equal to mc square. So this is the famous relation given by Einstein. The mass of the particle measured in frame of the reference in which the particle is at a rest is called rest mass. So let us consider this mass is there, and the basically mass when it is at a rest. So the most of the mass can be measured at a rest, and that can be considered as m naught, and it is known as rest mass. Rest mass. The rest mass energy of the particle would be, so if you want to find the rest mass energy, so we can write that m naught into c square, because we are using the rest mass, which is enormously large on an account of the large body of the sea. Now, if I is the kinetic energy of the particle, then the total energy. Now, let us consider if I is the kinetic energy of the object. So, let us consider E is equal to mc square is the total energy of the object. So, in total energy, it has some rest mass energy, and if you we can say that it is rest mass energy, and it has some, since it is moving, so it has some kinetic energy. So finally we can say that m naught c square plus kinetic energy is equal to total energy. When m is called the effective mass, m is considered as effective mass, and it will be effective mass, since rest mass as well as it is includes kinetic energy, and this will be equal to mc square. So if we convert in the form of a overall rest mass overall, so effective mass can m is considered as greater than the m naught, right? Now let us talk about the nuclear binding energy. So this is again one of the important topic, that is nuclear binding energy. The sum of the masses of the neutron and a proton forming a nucleus is more than the actual mass of the nucleus. Now let us consider five protons are there, five neutrons are there, and when they, so let us consider there is a mass m1, that is initial mass. Now when it has been formed 5 proton and 5 neutron, when it combines, so it will create a nucleus, right? So now nucleus has a final mass, and it is considered as a m. Now it has been considered that the initial mass is greater than the final mass. It means that initial mass is greater than the final mass. It means that after combination where the other mass went down, m initial minus m final is equal to the sum mass which has been, so there is a less mass, so where this less mass went out, so this less mass is considered as the mass defect, right? Okay. Now The thing is that in a certain number of the neutrons and protons are brought together to form the nucleus of a certain change, and the mass and energy P will be released in this process. So energy P is called the binding energy of the nucleus. Now let us consider there is a two mass. So there is a one mass, or there is a nucleus and there is another nucleus, that is equal to 5 neutron and 5 proton. Now when they are tied together, so what will happen? Energy will be released, and this energy is called the binding energy of the nucleus. Now this, from where their binding energy comes, so this binding energy will become as the E is equal to E binding is equal to m into c square. But what is from where this mass came out? So earlier the mass was, initial mass was I and final mass was mf. So the change in a mass is equal to delta m and into c square. So this is called the binding energy. So I hope you have understood this, right? So finally we have got the binding energy from this, okay, where delta m is the mass defect. Okay, now how to find a delta m? So you can find delta m. We need to find a delta m? So let us write one by one. So this 5 proton, I am just giving you an example, not exactly the 5 neutrons. So when they will combine, so it has initial mass, and after combination of 5 proton as well as 5 neutron, what will happen? Energy will be released. Energy will be released, and this energy is called as a binding energy, right? Now it has some sort of mass, that is final mass. Now mass defect, that is delta m, will be equal to m initial minus m final, right? So finally, if you find the energy, binding energy, so binding energy is equal to delta m into c square. But what is delta m? Now delta m is the z into mass of the proton plus a minus z into mass of the neutron minus total mass is equal to c. So this is the formula for binding. So mass defect, we can easily find out by this formula, we can easily find out the mass defect, right? So this is considered as a mass defect. So I hope you have understood this. Now where m is the, see, one more thing, m is the mass of the nucleus, m is the mass of the nucleus, mp is the mass of the proton, and mn is the mass of the neutron. So the see here, this mass defect reappears as an equivalent energy, that is delta mc square, which is liberating during the formation of the nucleus. Conversely, the amount of delta mc square is an external energy is required to break the nucleus into the protons and neutrons. Now let us consider there is a neutron and a proton. 5 neutrons and 5 protons are there, and they are in the form of a nucleus. Now nucleus, now when they combine, so we have got the energy. Now if you want to break it up, so what will happen? We need to provide energy, and this energy will be just equal to the binding energy itself. So the binding energy of the nucleus is defined as the minimum energy required to separate the nucleons. So this is a very simple definition. So binding energy eb, that is binding energy is minimum energy required, minimum energy required to separate its nucleons. I hope you have understood this. Now what is average binding energy per nucleons? Now let us consider it has a 5 protons and 5 neutrons, and it has binding energy Eb. But I want the binding energy per nucleons. Binding energy per nucleons. I want binding energy required to bind one nucleons. This will be equal to total binding energy divided by the total mass number, because mass number, that is A is equal to number of proton plus number of neutron, that is mass number, right? Mass number. So binding energy per nucleons can be written like this: EBN by EB by N is equal to EB by atomic mass number. Now let's do some sort of questions before that. A given coin has a mass of 3 gram. Okay. Calculate the nuclear energy that would be required to separate all the neutrons and protons. That is, they are asking a binding energy. For simplicity, assume that coin is entirely made up of a copper and the copper has atomic mass like this. So how to proceed this one? So we need binding energy, right? So again we need to binding energy. For this, what we need to use the formula. So before that, we need to what they have provided. So given mass of the coin is 3 gram, atomic mass of the copper is 63. So the mass of the copper is 2963 is equal to this u, right? Now the Avogadro number is this one. So mass of proton will be this one and mass of neutron is this one. So this you should memorize it. So the nuclear energy required to separate will be EB. Now we know that the delta M is equal to Z into Z is the atomic number. Atomic number and A minus Z. So A is the mass number, right? So atomic number. So this will be the mass of proton and this number is the mass of neutron minus mass of the nucleus. So see here, mass of the nucleus is how much? 62.9206. It is given, and mass of neutron, mass of proton and neutron is given. So total mass when they are in a separate minus total mass in a when they are in a combined form. So we will get this. We have got 0.591935, right? So try to be accurate. Otherwise, there will be a different result. Okay. Now, number of atoms in a 3 gram of a coin is how much? 6.023 into 10 power 23 into 3 divided by 63. So, this is just a Avogadro number. So, you will get the number of atoms in 3 gram. Now, the total mass. So, for one atom, we have this mass. So, the amount of atom is this. So, we have total mass like just you multiply it with the number of atom only, because for one atom we have got this mass. Defect for a total for 3 gram of a coin, we can say that the total mass is 1.6977 into 10 power 22. So the nuclear energy, binding energy to separate this will be delta m into c square. So delta m into c square into 931 mega electron volt per c square. So from here we can write, or we can just multiply it. So you will get the values. So I hope you have understood this. Now let us do next question, that is find the binding energy of per nucleus. So they are asking not only binding energy, they are asking binding energy per nucleons. So before that, we need to find the binding energy, right? What they have given, calcium 2040. So mass of the mass, that is they have provided you the capital M, that is mass M, that is equal to 39.962589. Mass of neutron and protons are given. Take one atomic mass unit is equal to 931 mega electron volt per cells C square. Now see here, we can just put one by one. A number of proton 20, number of neutron 20. So total mass of 20 proton and neutron will be 20 proton plus 20 neutron. So this is this one. So total mass of mass when they are in a separate. So mass defect will be the total mass when they are in a separate by total mass when they are in combined form. Why this is, I have kept this because they have provided these values of the mass of the nucleus of the calcium. So the mass defect is this one, such we have got this. Now total energy will be this defect into 931. So this will be 3 mega binding energy like this. So binding energy per nucleon. So number of nucleons is 40. So from here we will get as binding energy per nucleons as a 8.547 mega electron volt per nucleons. I hope you have understood this now. Now let us discuss about the binding energy curve. Now this is very important curve. Most of the questions will come from this. It is a plot of a binding energy per nucleons versus their mass number. Now let us consider there is a mass number, right? For example, if we consider about the hydrogen, and it has a binding energy per nucleon, and let us consider about the iron, it has also binding energy per neutron, per nucleons, as well as uranium, it has also binding energy per nucleon. Now it has been observed that the binding energy per nucleon is very high, sorry, very low, very low for the hydrogen atom. After that, suddenly what will happen? There is an increase in the binding energy per nucleons to the helium. After that, it will little bit decrease. So after that, you will find that for iron, it will be maximum binding energy per nucleons. After that, what happens? Uranium, there will be little bit less binding energy per nucleon for the uranium. Now, as soon as the atoms are more closer, what happens? There is a very strong bond, and it means that it has more stronger binding energy per nucleons. But as soon as we go for the iron also, sorry, it is very less binding energy because it is very less atoms. Now as soon as the number of nucleons will increase, so what will happen? The size will increase, so what will happen? It will create more binding energy. So for iron, it will be have a maximum binding energy. For iron, it will have a maximum binding energy. But as soon as when we go for the uranium, so what happens? Due to large size, what will happen? A nuclear force of attraction will decrease certainly. And when nuclear force of attraction will decrease due to its large size, so there is a certain drop in the binding energy per nucleon. So that's why from this we can conclude that the graph suddenly it will increase, after that it will little bit decrease, after that this will come like this only. Okay, so I hope you have understood this. So this is the binding energy curve for the per nucleons. Now what are the features from the plot? Average binding energy for the lighter nuclei like hydrogen is very small. For a mass number ranging from 2 to 20, there are simply defined peak, that is H2, C6, O8, 16. The peak indicates that the nuclei are relatively more stable than the other nuclei in their neighborhood. Now, binding energy curve has a broad maximum peak in the range of 830 to A130, which is practically constant corresponding to the average binding energy. So from here, the regions, see, binding energies are overall same when the peaks are broad, but when there is a no conical peak, so it means that the binding energy suddenly decrease, suddenly increase. Now, as the mass number increase, the binding energy of the nucleon decrease gradually, falling about 7.6 mega electron volt per nucleon for the uranium. The decrease may be due to the Coulomb's repulsion between the proton. As the uranium size is very high, so what will happen? There is a proton and proton, so there will be repulsion. And you know that the nuclear force is the less range force. So whenever size will increase, so what will happen? The binding energy per nucleons will increase, right? So from here we can get some of the conclusion. Following are the conclusion obtained for the graph. So a very heavy nucleus like A is equal to 240 has a lower binding energy per nucleon as compared to the nucleus of the A is equal to 20, mass number having a 120 mass number. This if A 240 breaks into two A nuclei, so nuclei gets more tightly bound. See here, there is a element having a atomic mass number 240, so it has binding energy per nucleon, so EBN, some EBN. Now when it broke into two, so it will get a 120 atomic mass number. So what we have observed, as compared to the 120, the binding energy for the 240 is very high, very less. See here, from this we can say that we can observe that the binding energy around the 120 is greater as compared to the binding energy of a 240. So from this what we observe that this is more unstable. See, if there is a heavy nuclei like a uranium, so it is unstable. but when it break into two parts, so it will become, it will be more tightly, this hole will be get more tightly packed, because it has a less number of nucleons as compared to the uranium. So it has a more binding energy per nucleons, and it has also more binding energy per nucleons. From this we can say that the binding energy per nucleons after the after breakdown become more stronger. That's why n binding energy per nucleons will increase. When two light nuclei A less than 1 join to form a heavier nucleus, fused heavy nuclei is more than the binding energy of the lighter nuclei. Now let us consider about the hydrogen. So hydrogen H1 and H1. So when they have a binding energy per nucleon which is very less, but as soon as they will combine to form a lithium and all or helium, so what will happen, its binding energy per nucleons will become very high. So it means that earlier it has less stable, but after combination or after fusion we can say that it is more stable, it is more stable. So I hope you have understood this. Now we will talk about the nuclear stability. Stability of nucleus is determined by the value of its binding energy per nucleon. Higher the binding energy of the per nucleon, more stable is the nucleon. So we have already discussed these things. So the stability of the nucleus is also determined by its neutron proton ratio. Neutron divided by proton ratio. Plot number of neutrons and number of protons as shown in a figure below. The solid line shows the nucleon with the equal number of proton. Only light nuclei are on this line, and that is they are stable, and if they contain approximately same number of protons and neutrons. Now let us consider, when we talk about the uranium, so number of neutron is very much greater than the number of proton, but when we talk about the iron, so number of neutron is approximately equal, little bit less than the proton for the iron or Fe, right? So it means that it is more stable, less stable, and it is more stable. So basically, when we saw the graph of the number of neutrons divided by number of protons, so in this straight line, number of neutron is equal to number of proton will be there. So this will be more stable, more stable. But as soon as number of neutrons will increase, so what will happen? Unstable element will form. So uranium may found in this, but when we talk about the iron, so it will found in this. Calcium, it may found in this line. So basically, for stability, number of neutron must be equal to the number of proton, or it will be a very less difference. The ratio should be greater than 1, right? So heavy nuclei are stable only when they have a more neutron than the protons. The long narrow region shows no, it is not correct. See, the thing is that heavy nuclei are unstable. Why? Because number of neutrons are greater than protons, so these are unstable. Like uranium, uranium are unstable. Uranium are unstable. Uranium are unstable, right? I hope you have understood this. Now let us go for the nuclear force from now see. Now I will talk about the nuclear force. What is nuclear force? From binding energy curve, we have seen that the average mass of the nuclei, the binding energy per nucleon is approximately 8 mega electron volt, which is much larger than the binding energy of the atom. Thus, the binding energy of the nucleus together, there must be a strong attractive force totally. So we can say that the binding energy of the nucleons, that is proton neutrons, is very stronger, as the binding energy per nucleons is very high, that is approximately equal to 8 mega electron volt, which is very large as compared to the proton and neutron, that is attraction between electron as well as the nucleus. So it means that the nuclear energy is more, nuclear force is very large. Nuclear force is very large, right? Nuclear force is very large, right? Binding energy together, there must be a strong attractive force of the totally different kind. Now let us see. It has been observed that the energy, binding energy or the nuclear force, see the force must be strong enough to overcome the repulsion. See, whenever there is a proton as well as proton, there is also proton. So in nucleus there will be a repulsion. Repulsion. So which force will bind together? So that force is a nuclear force and nuclear force, and this force must be stronger than the repulsive force. Then only they both will get together. So it means that the constancy of a binding energy per nucleus is a consequences of the fact that the nuclear force is short range force. So nuclear force are these are short range force, right? From the plot, it is concluded that the potential energy is minimum at a distance this, and which means that the force is attractive for a distance larger than zero point 0.8 Fermi and repulsive for the distance less than zero point 0.8 Fermi. Now see here, the thing is that the nuclear force is very strong whenever it will be come in a less distance, that is short range force. Short range force, right? Now, some important characteristics of these forces are given below. Nuclear force among the pair of neutrons, a pair of protons, or also between neutron-proton pair is approximately the same, and this is shown that the nuclear force are independent of the charge. It doesn't depend upon the charge. Next is nuclear force are very short range force. Whenever neutron-proton will come at a very less distance, then only it will create a force. Nuclear force is much stronger than the Coulomb's force acting between the charge and the gravitational force. Now, nuclear force between two nucleons falls rapidly from zero as their distance is more uh, a few femtometers. This led to the saturation of the force in a medium of or a large size nucleus, that is the nucleon interacts with the immediate neighbor only rather than with the all other nucleons. So it means that neutron, this is the neutron, this is, let us consider this is a neutron and this side there is a proton. So it will only get attracted or by the nuclear force which is at a short range. It means it will only interact with the neighbor force. It cannot be, if neutron is here and there is a proton and there is again neutron, so there will be no attraction or repulsion between these two. Why? Because this is long range force and nuclear force will only act when they are at a very less distance only. So nuclear force are see, nuclear force are short range force, and nuclear force are dependent on a spin or a angular momentum of the nuclei. So I hope you have understood this. So I will discuss nuclear energy in the next topic, next part of the video. Thank you for watching my video.